Hey everyone, starting chapter 25, which is a continuation after. In chapter 24, we saw that light consists of oscillating electric and magnetic fields. Together they make up light, and now we can see how light itself behaves once you've made it. So we're going to look at the reflection of light specifically, or what happens anytime light encounters mirrors. So a question I want you to be thinking about is, why is it harder to see the road in the rain? I don't know if you've noticed when you're driving, you turn your headlights on and it's almost like they're not on. It's really hard to see the road. And yet, cars that are coming towards you suddenly seem brighter, like there's a glare in your eyes. That has to do with this reflection of light. So first, we're going to need a little background. First section is looking at wavefronts and rays. So if we imagine a sound wave that's being emitted by a pulsating sphere, that just means that it's uniformly emitting sound in all directions. And so the sound would come outward in these spherical shells, right, that are uniform in all directions as it gets bigger and bigger. Those are known as the wavefronts, right? Here they're drawn as hemispheres, as half of the shell, but you can imagine there's the other half on there as well, that the sound is just going in all directions. And those wavefronts are separated by the wavelength, lambda, which shows the distance from one peak to another peak, or one crest to another crest. You can picture this if you go to the ocean, when there's a set of waves coming in, you can see the crest of one wave coming, and then there's another wave following behind it. And the distance between those is just the wavelength, the length of how long that wave is. So that gives you a description of the wavefront, of how the wave of sound or light could move in all directions. But what we're often going to shift towards is instead drawing these straight lines, much easier to draw than a hemisphere. And these straight lines we call rays. And the rays we draw perpendicular to the wavefronts. So we show how the light starts at the pulsating sphere or the sound, and that wave moves outward radially, right? And the rays are drawn in all directions because the light is going in all directions, but we're just drawing a single straight line, which is often much easier. So that's part of why we use rays. Now, as you're close to the pulsating sphere, the wavefronts are pretty curved and spherical, like we saw in the last one. But as you start moving further and further away, the wavefronts start to become flatter and flatter, or they become like a plane, where a plane is just a totally flat surface. So that's something you could be imagining there. And if you notice the rays start out pretty angled from each other, but then as you get really far away, the rays are essentially parallel. So that's something we want to hold in mind. And anytime you see drawings that have these rays, these arrows, you can imagine they're just showing how the wave itself is moving in that direction. Right, so that set the stage for us now to get to section 25.2, which is looking at the reflection of light. And the big idea here that we're going to see in several different instances is this law of reflection. It says the incident ray, the reflected ray, the normal to the surface all lie on the same plane, and the angle of incidence equals the angle of reflection. That's the key detail. Theta r, the angle of reflection, must be the same as whatever theta incident is. And that's depicted here where we have a mirror and there's an incident light ray. You can imagine shining a laser, for instance, but this works for other light sources too. Laser's just the easiest to see. So we shine our laser pointer at the mirror and then it reflects off of the mirror, and it's at the same angle being reflected, theta sub r versus theta sub I. Now, a key detail here is these two angles are defined relative to the normal of the mirror, relative to that perpendicular of the mirror surface. So anytime you have a problem, I recommend first drawing in that normal, right? Because you could have it where maybe it's a vertical mirror, right? Something like that, where we have a nice vertical mirror and a light ray comes in from above. And that might be all that's given to you on the problem. Here, I'll stop sharing for a moment so you can see a little easier. That might be all that's given to you on the problem. Well, then it's not clear if you want the angle next to the mirror or something else. So that's why I recommend starting by first drawing in the normal, which is going to be, hey, wherever this light ray meets the mirror, we want to draw the perpendicular dotted line pointing out. Because our theta sub I, our incident light ray angle, will be defined relative to this normal. So that's our theta sub I. And then we know that the reflected light, the light that bounces off the mirror, is going to reflect outward at the same angle. We could call theta sub R. Sorry, that's really small, but I promise it's the same as what's in the slide. That's the reflected versus the incident. My angle marking there. It's a little bigger, theta sub R versus theta sub I, and these two angles again have to be equal. So that's the big idea here, and you notice we're focused in on just drawing those rays because that's going to be the very easiest way to do it. All right, so let's go back to sharing. Whoop. There we go. Okay. So that's what's described here in the law of reflection. That simple equation, but the key is how you use it. Now, in specular reflection, the reflected rays are parallel to each other. So if you have this really smooth surface like a mirror, then as the light ray comes in, it reflects off following the law of reflection, and all of them bounce off at the same angle. So the incoming light rays are parallel, the reflected rays are parallel. In contrast, diffuse reflection is if you're coming in towards a rough surface, something that's not smooth, then the light rays are still going to follow the law of reflection, where they reflect out at the same angle relative to the normal as in, but the normal now is in completely different directions. It's not just straight up and down as it was before with the specular. And so what will happen here then is some of the light rays will point on forward, others will point upward, they could even point straight backward depending on the rough surface here. And this is what happens when it rains, or the contrast between normal conditions and otherwise. Because normally if you're driving on asphalt or concrete is a pretty rough surface, and that's intentionally so, because then some of your light rays are able to reflect back to you and you're able to light up the road and see the light. It makes it to your eyes. But when it rains, all of those rough pieces of the asphalt get filled in and they get totally smoothed over as though it's a mirror. And so you send your light rays in of your headlights and they reflect downward to instead blind oncoming traffic, and they don't reflect back to your eyes. So it no longer looks lighter. So keep that in mind. Next time you're driving in the rain, you can check it out. It has to do with the reflection of the light.